Consider these two sets, the set of integers and the set of polynomials in X over rational numbers. We have studied these two sets, and we have learned that these are both rings. But not just rings, but they are commutative rings. That means their products commute. Commutative rings. But actually, they are not just commutative rings. They have, in addition, they have the multiplicative identity elements, and also they have no proper divisors of zero. In other words, they are both integral domains. But not only that, still, we have seen more common properties of these two sets that are they have both division algorithms. Division algorithm. And therefore, we could derive the Euclidean algorithm. To find the greatest common divisors. Either greatest common divisors of two integers or greatest common divisor of two polynomials. So we can be more specific than saying they are just integral domains, but they admit the division algorithm or Euclidean algorithm. So let us abstract these concepts. That means integral domains that admit division algorithm or Euclidean algorithm, and define some new notion. That is, we define Euclidean domains. But rather than just saying Euclidean domain is an integral domain that admits division algorithm, we define a Euclidean domain in the following manner. First of all, let D be an integral domain. And suppose there exists a mapping V from D except for the zero element to the set of natural numbers including zero. Okay, so non-negative integers, such that this mapping has the following properties. One, for all elements A and B in this D except for 0, we have V of A is less than or equal to V of A times B. Okay, the result of this mapping is an integer, non-negative integer. So we can just understand this inequality as an inequality between two integers. And two, for all AB in D except for 0, there exists elements Q and R in D such that we have A is equal to BQ BQ plus R, where we have either R is equal to 0 or if R is not 0, then v of r is less than v of b. Okay, so basically we are saying that we have some kind of the division algorithm, but in this case we are not comparing this remainder with this b directly, but in terms of this function, this mapping v. Okay. So anyway, a Euclidean domain is an integral domain such that there exists a mapping from d except for 0 to non-negative integers such that these two properties are satisfied. Okay. Let's see a few examples. First of all, z. We know that this the set of integers is a Euclidean domain. Okay, so in this case, what is the mapping v? In this case, we define this mapping d by just absolute value of the argument. Okay, where a is an integer that is not 0. Okay, so let's see if this mapping satisfies these two properties. Okay, first of all, we have v a b, and we are assuming a and b are not 0. By definition, this is ab absolute value of ab, but this is equal to the product of the absolute values of a and b. But since a and b are integers, non-zero integers, this is both of them are greater than or equal to 1. Therefore, this is greater than or equal to the absolute value of a, but this is equal to v of a. So the first condition is satisfied. And the second condition, that is just a division algorithm. Which we know is true for the set of integers. So therefore, the set of integers is a Euclidean domain. And another example, consider the set of polynomials in X over F, where F is any field, such as rational numbers or real numbers or complex numbers, any field. Okay, then this is a Euclidean domain. Let's show this. So what is that mapping v? Suppose f of x is an polynomial with coefficients in f. Then we define the mapping v of f of x as the degree of the polynomial. Okay. And we assume, of course, this is not 0. And so let's show this mapping v satisfies the required properties. First of all, suppose f and g are polynomials. So v of f of x times g of x. So they are non-zero polynomials. And this is the degree of the product. And as we have seen, the degree of a product of two polynomials is the sum of the degrees of their components, degree of g of x. And So these are integers greater than or equal to 0. So therefore this is greater than or equal to the degree of f of x. But this is by definition v of f of x. Therefore the first condition is satisfied. And the second condition, we know that for a polynomial ring we can uh, derive the division algorithm. Algorithm. That is, so if we have any polynomials a of x and b of x, then there exists some polynomials q of x and r of x that satisfy the required conditions. This. So therefore, this is a Euclidean Euclidean domain. Let's see a little bit more concrete example. Consider z5 of x. So this is a set of polynomials in x over z5. And since 5 is a prime number, z5 is a field, as we have seen before. Therefore, this is a Euclidean domain. Okay, so let's see an example. If we consider a of x as, let's see, 3x to the power of 4 and 2x to the power of 3 and 2x squared and x plus 3 and b of x squared plus 2. Then we can show that you should verify a of x is equal to b of x times, let's see, 3x squared 2x plus 1 plus 2x plus 1. So this part will be q of x, the quotient, and this part will be r of x, the remainder. Next, let's prove a little lemma. Let D be a Euclidean domain. With the identity element 1. Okay, then for all elements of D except for 0, we have v of 1 less than or equal to v of a. And second, for all elements of D except for 0, we have v of 1 is equal to, so this is less than or equal, okay? And the second says the condition for this equality, v of a is equal to v of a, v of 1 is equal to v of a, if and only if a is a unit of D. Okay, so what is a unit? Unit is a, so let's say a is a unit. Basically, it is an invertible element. So by definition, if there exists some element in D such that a, b is equal to 1. Okay, in other words, if there exists a multiplicative inverse of the element, then that element is called a unit. So let's prove this. And the first one is very easy. For any element of D except for 0, let's see, V of A is equal to V of 1 times A. But by the definition of this mapping V, this is greater than or equal to V of 1. And it's done. So this is part 1, and this is next part is part 2. So since this is if and only if statement, we have to prove both directions. Okay, so let's prove if part first. Okay, so suppose A is a unit. Then by the definition of unit, there exists some B such that AB is equal to 1. Okay, so V of A is less than or equal to V of AB, but this is equal to 1 because of this, right? And from part 1, V of A is greater than or equal to V of 1, but here we have V of A is less than or equal to V of 1. Therefore, V of A is equal to V of 1. Then we prove the only if part. So suppose, so what is it? Okay, this is assumed. So suppose V of 1 is equal to V of A. Then we want to show that A is a unit of D. Okay, and according to by the division algorithm, since we are assuming D is a Euclidean domain, we can assume the division algorithm. Division algorithm, there exists some Q and R, which are elements of D, such that 1 is equal to A times Q plus R. Okay, and suppose R is not 0. Okay, so this remainder is not 0. Then by the way we define the division algorithm, this R must the V of R must be less than V of A. But by assumption, V of A is equal to V of 1. However, according to part 1, this cannot happen. So for every A, V of A is greater than or equal to V of 1. So if for any element R, V of R is less than V of 1, this cannot happen. So this is a contradiction. Therefore, R must be equal to 0. Then we have 1 is equal to A times Q, which means A is a unit. And we are done. Next, consider a subset of complex numbers, which we denote as Z of I. Okay, that is defined as, let's see, M plus Ni, where M and N are integers. and I here is the imaginary unit. And the complex numbers of this form, m plus ni, where m and n are integers, they are called Gaussian integers. Now, let's provide another lemma that says z of I is a integral domain. Okay, so an integral domain is a commutative ring with the identity element without proper divisors of 0. So first of all, we should note that z of I is a subset of the set of complex numbers. And the set of complex numbers is a field, which is a ring. So first we should show that this set, the set of Gaussian integers, is a ring. So to do so, we can use the subring criterion. Okay, so let's check whether this is closed under addition. So let's see, m1 plus n1I, m2 plus n2I. So suppose these are elements of z of I. Then let's add them. So just like adding two complex numbers, we can add m1 plus m2 plus n1 plus n2I, which is clearly an element of z of I. So it's closed under addition. And then for m plus ni in z of I, we can, its additive inverse is of course negative m minus ni. So m plus ni plus negative m minus negative ni is equal to 0. So there is always an additive inverse. Okay, and of course this is an element of z of I. And what about multiplication? m1 and n1I times n2 plus n2I. This is m1 m2 minus n1 n2 plus m1 n2 plus n1 m2I. So these are integers, so this is an element of z of I. Therefore, this is a ring. Okay, so additionally, we need to prove it is commutative, but commutativity is clear because this is just a multiplication of two complex numbers, and complex numbers are a field, so it's a commutative ring. So that's fine. And the existence of identity, that's clear because it's a field, and there is the identity element 1. This is an element of z of I. And the absence of proper divisors of 0 is also clear because C is a field. So there are no non-zero Gaussian integers, the product of which can be 0. So we are done. Next, based on this lemma, we prove the following theorem. That is, z of I, the set of Gaussian integers, is a Euclidean domain. With the function, the mapping v, defined as the squared absolute value of a. Of course, a is a element of z of I except for 0. Now let's prove this. What we need to prove is the two properties which this mapping V must satisfy. Okay, so let B be an element of Z of I, and which is not 0. Okay, then the value of V of B is equal to B modulus squared, and that is B1 squared plus B2 squared. Since B1 and B2 are integers, this is greater than or equal to 1. Okay, so VAB is equal to AB squared, which is A squared modulus squared and B modulus squared, which is less than or equal to, greater than or equal to A modulus squared, which is equal to V of A. So the first property is satisfied. And second property, let's say A and B are elements of Z of I except for 0. Then we want to find, okay, then we want to find Q and R such that A is equal to BQ plus R. Okay, let's consider A over B and express it as alpha plus beta I. And this is, in general, this is not a Gaussian integer, but alpha and beta are, at least, they are rational numbers. Okay, and let's express alpha as a sum of an integer that is closest to alpha plus epsilon, which is a rational number. So, okay, so let alpha be this and beta be n plus eta, such that m and n are integers and epsilon is its absolute value is less than 1/2, because m is the closest integer to alpha, and eta's absolute value is less than 1/2, and for the same reason. Okay, then we have A over B as, so replace alpha with this, beta with this, we have n plus epsilon, n plus eta I, and m plus ni, and epsilon plus eta I. Okay, and let's define this part as Q. Okay, and Q is, of course, Gaussian integer. Okay, so we have A is equal to BQ plus B epsilon eta I. So let us define R as A minus BQ. So from this expression, it is clear that R is a Gaussian integer. Okay, because A, B, Q, they are all Gaussian integers. Therefore, this results in a Gaussian integer. And now, using this expression, we have BQ plus B epsilon eta I minus BQ. So BQ are cancelled. We have B epsilon eta I. Now, if this R is 0, then we are done. And if it's not 0, then let's calculate the value of V of R. So by definition, this is B epsilon plus eta I squared, and this is B squared and epsilon plus eta I squared, and this is wait a minute, this squared and eta squared, but by the way we define epsilon and eta, they are both less than 1/2. So this is less than or equal B squared, so 1/2 squared and 1/2 squared, and this is equal to B squared. So this is 1/4 plus 1/4, this is 1/2, and this is less than B squared, which is the value of V of B. So therefore, we have found appropriate Q and R found. And we are done. Let's see an example. So let's say A is equal to 5 plus 6i and B is 2 minus 3i. And we want to find Q and R such that A is equal to BQ plus R. And Q and R are Gaussian integers. So just following the procedure we have described in the proof of the previous theorem, let's calculate A over B first. And that is 5 6i over 2 minus 3i. And by multiplying the complex conjugate of the denominator to both numerator and denominator, we have, let's see, 5 plus 6i, 2 plus 3i. And after all, this should be negative 8 over 13 plus 27 over 13i. Okay, and the closest integer to this is -1, and the closest integer to the imaginary part is +2. So let us define Q equal to -1 plus 2i. 2i. Okay. Then R is A minus BQ. So that is 5 plus 6i minus 2 minus 3i and negative 1 plus 2i. So if you calculate this, let's see, 5 6i minus, what is it, 2 negative 2 positive 6, so that is 4 and negative 3 negative 1, that's positive 3 and positive 4, so that will be 7i, and the result is 1 minus I. Okay, now the absolute value of R is, let's square it, and that is 2. And the absolute value of B squared is, what is it? So that is 2 squared plus 3 squared. That is 13. So this is less than 13. So sure enough, we have this form where v of r is less than or equal to v of b. And we are done. Okay, let's express the final form. 5 plus 6i is equal to 2 minus 3i times negative 1 plus 2i plus 1 minus I. So all of these are Gaussian integers.